All right, we have our final question for this chapter. Let's go ahead and get it done. The statement, find the Lorentz gauge potentials in the fields of a time-dependent ideal electric dipole P of T at the origin. It is stationary, but its magnitude and or direction are changing with time. He is foreshadowing so hard with this question. Don't bother with the contact term. Next chapter, you will see this over and over and over again. So, brace yourself for impact. All of this is highlighting what's coming next. The retarded potentials are, if that's the case, we have V, R of T, and A, R, and T as such. Again, with the retarded, evaluate at the retarded time. And we want some source localized at the origin, so we expand in powers of R prime, keeping the terms up to the first order. Script R squared goes to R minus R prime dot R minus R prime. Factor that out with the dot products accordingly. And since that's the origin, we get rid of the R prime there. And we kind of simplify that approximation down to R squared minus 2R dot R hat, or R prime. Okay, so take the square root, factor out the R squared, and now apply the approximation that we've seen before, the binomial expansion for the square root. Gosh, that thing has been a pain in our butts, but guess what? It's coming back again in full force next chapter. Similarly, again, go ahead and apply the binomial expansion, which all that results to is the plus sign on the inside of the bracket and flipping that 1 over R on its head. So with that, T minus R over C for the retarded time gives us a T naught plus R dot R prime RC. Okay, we've seen this before. Nothing too ridiculous, but definitely can be a mess. Alright, so where T naught is equal to T minus R over C is the retarded time for a source at the origin, thus Taylor expanding about T naught. We've seen this charge distribution happen before, so we won't spend too much time on it, but we also see that dividing by the script R for what we need in the integral yields to this grossness that we have to clean up. So we will do that, and then we'll expand, and we're only going to keep first order terms. So you see what happens after that foiling and distributing. So now that we have the argument or the integrand for that integral, let's go ahead and plug it in, and go ahead and split up the terms that we have. So we got 1 over R over R cubed. Just tidy it up and let the integrals do their work. The first integral is the total charge of the dipole, which is 0, because it's a dipole. The charge is summed to 0. And so the second integral is the dipole moment, which we've seen that before. And the third is the time derivative of the dipole moment. So, similarly for the vector potential, we do the expansion of the current density and then around T naught. And we see that we get mu naught over 4 pi P dot at the retarded time T naught over R. Okay, so from equation 5.31, we see that the integral gives us the P dot at T. And that J is equal to rho V prime, which is equal to dx prime over dt. And this is already in the first order for R prime, so the second and third integrals are second order, and we drop them. Again, we're going to use these arguments a lot in next chapter. In calculating the fields, remember that the dipole moments themselves depend on R. Through their arguments, T naught equals T minus R over C for a function of T naught alone. So here we're just setting up the general form of what to expect with a function of T naught. So we have to go through F, hence the chain rule, onto T naught. And then we know that df at the retarded time just gives us f prime. And then T naught itself gives us a negative 1 over C, on its way to the gradient of R. So with that, if we're going to the gradient of R, we get negative 1 over C, f prime R hat. So if we simply replace the del operator with negative r hat over c d by dt, we know what we get. And so this has for the structure of the form f of t naught plus r over c f dot t naught. If we apply this exact rule, now we see that the del operator applies a time derivative to these things with that 1 over c factor. Kind of gross, but, makes sense. You got some more product rules to take into account, but everything is indeed coming together. So after that, we see a cancellation. So all we're left with is that double dot with the r vector over c squared. So for all the gradients of the scalar potential, we need to use the gradient of the dot product. And that gets gross real quick. Let's go ahead and see how that's running through. You see, again, some of these things that we want for the first order just won't work out. You see we got some zeros. Really no big deal thanks to that curl that we have. But what we need to do is put this in that coordinate-free form. Wrap it up nicely, so that's what we see in the last step with the 1 over 4 pi with the squiggly brackets. That's what we're aiming towards, so we simplify for that coordinate-free form. Similarly, the vector potential is surprisingly easier, since all we had was one thing in a bracket. Take the curl, allow the life to continue, simplify down by taking the time derivative of the vector potential, and now we know what E is, and you see the coordinate-free form there. And we see that B is also equal to something in a coordinate-free-esque form. And this is all gross. And this question is foreshadowing you for what's going to happen in the next chapter, where the scalar potential and the E fields are much worse than the B fields, surprisingly. But we'll see that soon enough.